Keeping up with the time, our last presentation for this session will be delivered by Dr. Mark Pawley to showcase the SADM, South Australia Discovery Mapping Project, our new geological compilation and data delivery system. Mark is a senior geologist with Geological Survey of South Australia who works on regional geological mapping and interpretation. He is heavily involved in the compilation and attribution of the spatial data for the Discovery Mapping Project. Let's hear from Mark.
Thanks, Amy. Now, you've heard quite a bit about the Discovery Mapping Project today. There's been a few references, and I think last year or year before, Megan Williams gave a talk on it. So it's actually been going for a while, but we feel now the project's at this, development stage where we actually talk about it as a whole. Previously, we had bits and pieces, but now it's all coming together. So I'd like to give you an overview of the project and then talk about some of the outcomes and how we see it evolving. In essence, South Australian Discovery Mapping is the solution to some problems. Ryan Dutch recognised that, you can see here, this is a screenshot from the Musgrave area. Our current digital map layers, they're edge match issues, they're different scales. This is just the factor that we digitise the maps available. So we have generational issues. So he sort of looked at this and thought, we need to make this better, and we need to sort of almost, if we could, start from scratch, and we're doing that as a test case. So we've got the edge match issues, different scales, different generations. We also have, because these are generated, the data associated with these, our current data, is generated from the maps. There's actually very little attribution. So if people are trying to do machine learning, this data isn't suitable. We have the issue that a lot of our data is spread across several systems within the government. You probably don't think it is a problem, but it does mean if we want to change something, change a polygon code, change the shape of a polygon, we have to actually go and talk to another branch. The person who knows how this system works may have left 10 years ago, and we sort of have this issue. So it's really hard to update that. So we have this, and this leads to the slow release of new data. And because of this slow release, we don't actually have the best available data we can. And just to sort of finalise the problems is the Gawler Challenge competitors, when they did that work, found that the data was non-seamless. This is some of the comments we made, and of course resolution. And the large part of the time was massaging the data into a form they could use. So what we don't want are the users, when they're exploring, to actually spend most of the time trying to work out what to do with it. If we can give it to them in a ready, steady state to go, then that would be ideal from our perspective and from yours. So we see the opportunities with the discovery mapping is to take control of our system. We're controlling how the data will be compiled, stored, released. We do a large part of this already, but we're sort of building the back end, which is the key part. This will give us the ability to update our spatial textual data, because again, we talked about legacy data just then. A lot of our information is actually in reports, which are PDFs and things. So we're actually going to digitise a lot of our information, as Meg referred to, and I'll mention again soon. And we'd like to generate data-rich geological information. We don't want a flat map. What we want is something that you guys can interrogate, play with. This came up yesterday at the workshop at the core library. If you're out there looking at the GP2, we're actually looking at data and how we can help you, and if you think data is a way of doing that. And also the new system means we can give you almost real-time data. So if our geochronologist dates a rock, we realise this Pluton in our solid geology is the wrong age, we can go in and change it, and almost once that's approved, it's done. So you can actually get those changes in real time. It's a big project. It's been going for a couple of years now, and it's going to be finalised by the middle of 2025. I'd like to stress that we're building a system that is not going to stop. The project doesn't stop at the middle of 2025. At that stage, we've built the system, the environment that we actually do all our work in the future. This is where we're going to compile all our spatial data, our explanatory notes, and all these extra types of information will actually be done within SADM. So this is really the way we're going to do all our work in the future. So it is quite a important project. I actually think it's really important because it's sort of, as a map compiler, this is actually adding a lot more to it than I could do if I just do it flat or I draw something. So I think it's a really important project. And it's a bit small to see on the right, but there's a lot of people involved in this work. This is I went through our governance document the other day. These are the people currently involved in the project, but there's actually a lot more. We've got Khalik Abdul, who's here. He was project manager for a while. This project is the outcome of a lot of work by a lot of people, some who have gone on. Because they've got good people, they get taken by industry and they get opportunities and they leave. So unfortunately, we lose people. So what is the components of the system? This was the original proposal. Looks quite complex, but really we have this is the back-end database. I'll describe all these in a moment. I'll just give you a bit of an overview. There's the map compilation team up here, the explanatory notes data team, there's the storage and then delivery. So I'll sort of go through each of those parts now. The back-end system, we're creating an enterprise database that has got a relational database within it. We're looking at service-based architecture, which is connected through web services. It's cloud-based deployment, and the compilation team is using ArcGIS Pro for their work. The digital explanatory notes is something Meg talked about, so I won't go too far into it. But all these stratigraphic unit descriptions are currently being reviewed, updated and rewritten. This is a big team involved, and Amy, who's chairing the session, is part of the team. We're also looking at updating the provinces, events and time slice descriptions. They're going to be updated or in some cases prepared. I'll explain what time slices are in a second. Importantly, the digital explanatory notes are no longer going to be a paper format. You could consider this, once it's all pulled together, will be like the digital green book. It can be updated, it's all related, so you can actually click on the spatial feature on the map, it'll take you to the explanatory notes for that unit. If you want to know about the location, you can go to the province, so you can delve as deep as you want into this information. We're trying to make it as user-friendly and as connected as we can. Now, the compilation spatial data, as Amy said, this is the area I'm familiar with, so I'll probably have a bit more time. I actually think this is really cool. We're doing some very interesting stuff, and it's also been a few big issues here to overcome before we can get this working. So we've got a new system. It's, as you said, compiling in ArcGIS Pro. We've got a lot more time slices. There's a one-to-many relationship, which you may go, what's that? Well, I'll go into that. Attribution is going through the roof. And we're introducing a standard vocabulary, which Christy mentioned, and I'll just sort of briefly go into as well. The time slices. Previously, we had 5 across the state. We've got 15, and the reason we did this is we want to actually have the data quite granular, so that when you do a search, you want to query, it's broken up in this way that you can actually extract information that's relevant to you. You don't get everything about the rest of the state. You can get the stuff you need. It's chronological approach, it's not depth slices. When I first started talking to people, they think as you go, say, older, you go deeper. That's not the case. It's actually about time. There's based on periods of, say, similar geological processes across the state, and then separated by periods where there's a relative quiescence. That doesn't work perfectly every time, but it sort of generally does the trick. And we've also got the situation where certain events have been differentiated. For example, there's a Tunduya time slice which we've thrown in, and this is basically the Hilltobit GRV magmatic event. So if you want information about that, it'll be its own separate time slice. There'll be a spatial layer that is solely dedicated to that one event. So we sort of tried to make it in a way that people can get what they want. And we feel that this greater flexibility is going to be better when you actually create maps. You can create the map you want rather than the map we decide you want, that you just get this flat thing. You can also then extract your own data. It's got a data-rich attribution. I've said it a few times, so I think this is one of the strengths. This is the data model we're working towards. We have the white tables are the attribute tables. So there's, as I said, it's a relational database, so features can have related to lots of tables, lots of different sets of attribution. We've got the validation tables, which contain all those fields in the vocab, and there's also the delivery. The attributes we've drawn for vocabularies, I'll go through that. Christy's mentioned it, and I think that's sort of something that's going to help you guys as well. This is just an example of some of the attribution we're now including. When you think previously, lines were generally, was it exposed, concealed, something about confidence, and usually what type. We've now got it, we can have kinematics. The one-to-many relationship means you can actually have one structure. You can record every event, where previously it was just the one. There was a one-to-one relationship, one line, one row of information. We've now got a lot more than that. Fault order, if you're looking for big second, first order structures. The geometry, which way is it dipping? Because it's the data will have orientation attribution, so you can do machine learning on which ways you want north trending faults of a certain age. You can do that type of thing. This is all being developed to help with queries. A lot of this stuff won't be necessarily be populated. For example, fault crustal depth. That will be really helpful in areas where we've got the seismic lines. If you can see there's a crustal scale structure versus upper crustal. The rest of the state, they may not be populated. So just be patient. We're populating them as we can, but as it goes, we're going to start adding to this and building it up and making it really quite a data-rich, vivid environment to work within. With the polygons, you can sort of see these are some of the attributes. Now there's information related to regolith, if it's Cenozoic. If it's igneous rock, you can do the redox state, fractionation state. Metamorphic grade, you can do a lot of different parameters, attribution, so grades, the age of that metamorphism. And from a mineral exploration perspective, there's also things like alteration style, alteration minerals intensity. So this could be based on drill hole, where sort of you can actually have within a polygon, you can have a point which will tell you that drill hole has got at this depth, this information, because it's all connected. So you can actually go back to the source. And just want to stress, this is something, because I usually work in maps, it's been a bit of a change in my thinking, but I'm not creating a map. While we've got all this attribution, they're related to spatial features, but there will be a lot of data that can be just taken out for its own use as machine learning. It's really about creating data. It's related back to a spatial feature, but it has inherent worth in its own right. And that's something I think is quite important to keep in mind, that we're generating data that is spatially related. The vocabulary, which Christy mentioned before, we're using standard vocabs. This it's something that's set using GSIML. International standards, these are across all our databases, which means you search for a search term in this database, it can find it in the others. Everything's standard, it's relatable, it's easy to find. So we've now got a harmonised system of databases, or that will be the aim by the end of the project. And the increased interoperability will enable the next generation of machine learning and hopefully mineral exploration. And you guys can use these tools. I think when I was sort of talking to Ursula about this, she said one of the things is they're looking at doing it internationally, so you can actually do it in different languages down the track. So it's something that, being standard, makes it quite a flexible system. Now, the one-to-many relationship was something that took a while to nut out, and I'll probably just sort of go through this in a bit. But what it means is when we draw a line, it can have several lines of attribution. In this simple case here, we've got a boundary line up here on the Pluton. That one line will have two lines of attribution because it's going to be related to a polygon, a rock unit, on two different time slices. So it actually ends up being two lines. One is this intrusive contact on this layer, and this is the age of the intruding rock, or the time slice intruding rock. Where it starts getting complicated is when you start getting structures. And that's the line running through here in the numbers. And in this case, the example is you've got a Peter Pan supersweet Pluton intruding Mulgathin complex, and that fault's been reactivated during the Kararan and the Kirby times at orogenies. Where you got the 1, 3, and 5, those segments will have two lines of attribution, one for each stage of movement. If it's known, they could be different kinematics, which is something I think is quite cool. It's related back to the event, so you can actually say at this time the fault did this, subsequently it did this. This could also be if you have a fault, let's say Rapina fault on the Eyre Peninsula, which has a fault scarp, it's got the Cenozoic expression. So you can actually start then tying it back to, say, surface features and looking really quite deeply at the history. But in the case of that structure, say number 4, because it forms a boundary, 4 and 2, they actually have the extra attribution for the contact. So this means they're coded as faulted contacts as well as structures. So if you're looking for a faulted contact of a certain age, of a certain lithology, you can generate a query that will give you all the locations where you can find those relationships. Now with the compilation, it's a two-pronged approach. There are a group who are actually incorporating the current best geology from the state. So this is there's some new mapping up in the Musgraves, the Campana basement geology from a few years ago that Tom Wise did, the Delamerian when that comes up. So that's incorporating our current best knowledge. But what we're also doing, and this is the role of the compilation team, there's a polygon, in regular one in black, and that's a test area we're working on. We're actually compiling using GCAS from scratch, using these, that data, but also the time slices and the attribution tools. So that's going to be our aspiration. That's going to be by the end of the project, middle of 2025, that will be compiled to the best of our ability. And that will be the aspiration of what we want to do. The rest of the state will be what we currently know. It's the best available data. So it'll be a bit of a Frankenstein until we can just progress and keep moving. Because as I said, this is not the end. Middle of 2025 is not the end of the project. It's the start. This is the build stage. We'll then be into the actual, let's get this maintaining data, adding new data. Now, delivery is something that's going to commence in early 2024. So we've got some broad ideas, but we don't really have a lot of specifics. But it will be all finalised by the middle of 2025. But delivery will be via SARIG and APIs, which are the digital waiters that Chrissy talked about. The maps will have attributed spatial features. There'll also be the data that's suitable for machine learning. And there's going to be online access to the digital explanatory notes. Now, just to give you a bit of an idea of the improvement in this area, so this is part of the area we've been compiling. You can see on the left is the GCAS data that was collected, I think not long before COVID, I can't remember the exact year. But on the right is the current solid geology from the 2 million geology we have. And you can see that it's pretty rough, and if anything, you look at the aeromagnetics, and I think everyone's going, wow, I do it very differently. I think we've got the opportunity to improve this. So in a time slice perspective, if you look from left to right, you've got the Archean Paleoprote time slice, so if you wanted to know about the Mulgathing rocks, you want to know about the Lake Harris Greenstone Belt, they're all included within this time slice. If you go to the middle one, that's the late Paleoprotes, so they're the, say, basins, the sedimentary rocks at Tarcoola, the associated basins, but also the Peter Pan supersuite Tunkilia. So if you're looking at those type of systems, you can go to this layer and get everything. And then on the right would be the Tunduya time slice, which is the Hiltuba. So if you're interested in that age of rocks, that package, you go to this and get it all. Now, while we're compiling and attributing in these time slices, we can just bring it together and just overlay them, and it becomes a seamless map. So this is the same area. Now, I've got the geology, the structural lines here. I haven't got the point where I've actually divided these into time slices. So when you think about it, some of these will be, say, Archean, that's time slice. Some will be the late Paleoprote if they're Kimban. Some, if they're Kararan, they'll be in that younger time slice. So when you think about the polygons I've divided, the lines will be the same way. And unfortunately, at this stage, I haven't got an example. But what we can do is, if we add them, we can create a full map. So it really depends on what you want. You can just do whatever, pull the pieces together, layer it, stack it, and interrogate anyway. Now, just to give you a bit of an idea, we're not just drawing lines and creating polygons. By the actual process of attribution is giving us a lot more understanding of the area than we probably previously had. On the right here is the current Archean early Mesoprote time slice that we release. So this is 2 million scale. Now, if you look across to on the left, it's the 1VD for the same area. And I think, again, you'll see, and you think, wow, you could do so much better if you looked at it, and you could, even just drawing lines on the screen, you'd do something very different. So what we've got is the opportunity, while we're doing this, is to actually pull it apart. So this is the line work I've drawn. I haven't, the pink is Mangilla granite, which was that magnetically low area up in the top right. But the line work is, I haven't actually put anything behind that. That's, so far, it's just going to be some Peter Sweet layered rocks and granites. But I just wanted to leave it blank so I could highlight the structures. But you can see a lot of information here. There's a lot of structures there, the black lines, a lot of shears, faults. You can see the foliation trends. So you can actually we'll be able to start to produce this information at a level where you can really start to understand the evolution of the geology of an area. And just to give you an idea, I'll just go back. So this area here on the right, just think there's very few structures, very few information, no folding, and we'll just see what we can now do with it. If you look, there's an obvious fold running through. I'll just think for location, that star is Penong, so this is just northwest of Ceduna. You can see there's this fold wrapping through, which is highlighted on the right. It's sort of quite a prominent feature. But when you actually zoom in to areas, if you zoom into this area on that limb, you can actually see there's closures. And if you look at there and there, and you go to the next slide, you can see there's actually a earlier generation of fold. So there's 2 stages of folding that we can pull out in this area. And you also then ask the question of, does that broad curvature of the F2, is there an F3? Or is that just reflecting? I've just drawn a continuous line, but is it actually a series of segments of offset folds, of offset fold hinges? So there's a few things there that still resolve. In the same area, if you go into this area, you can see that the early structure we saw, that's been folded, when you zoom into the area, you can see that there's actually truncation. So these are things you can map out. You can see where the layering's cut at a high angle. It's also got transposed layering wrapping around. So you can see that there's an early folded generation of shears. If you go up into this area, which is up in the fold hinge, I think it's quite cool because you've got the well-laid rocks highlight a lot of folding, but it's a very different wavelength to what's to the southeast. But also what you can see is there's actually an axial planar parallel shearing where the layering's truncated. So there's pre-folding or pre-F1. There's also syn-folding axial planar faulting. And then if we go into this, back to this area, we can see that there are sinistral faults that are offsetting all the previous structures. So when we go back to this, you can see what was originally there, what's originally believed on the left. On the right's the new structural interpretation. And we can see that between 1623, which is the age of the package of rocks that's been affected, a constrained age, 1580, which is the age of that pink Pluton, you've got 2 stages of folding and the first 2 generations of faulting and shearing. Following that, you've got the 3rd stage of faulting shearing, which could either be Kararan, late Kararan, or it could be Kirby. So you can actually start to unravel these. This will all be in the attribution, it'll all be related back to the spatial features, and you can all be able to interrogate this. So for the users, the benefits, there are a lot of benefits of this project, I believe. The extensive attributions, the lines and polygons will allow interrogation of the data. The increased number of time slices will allow greater flexibility when generating digital, I'll call them maps, but it's just going to be surfaces, geological spatial features. And when looking at those, and you can also create these time maps to your requirements, so it's very, very flexible. And you can also then extract the data related to that. So it's not just maps, it's data. The spatial data will be related to digital explanatory notes and other GSSA databases. So things like the geochem Lana just talked about that's been entered. You can do queries. Christy talked about this earlier when she showed an example. We'll also have the near real-time releases of updates. This will allow the quick incorporation of new results. And the data is going to be in a range of formats. This is suitable for machine learning, for viewing. Where previously the data was human readable, we're trying to make it machine readable. It's going to be released via web services, mobile applications. And I think one thing that's been worked on quite a bit is we want this system to be robust and flexible so that we can future-proof it. So that we can actually keep, as new ideas, new data come through, the system will evolve so that we constantly produce the best product for you guys. Thank you.